Hey, welcome! Today, we're diving into the hidden language of numbers. We're going to uncover the simple, almost secret rules that let us see how a pattern of numbers is going to play out way down the line. I mean, really think about that for a second. How can someone look at just a few numbers and tell you what the thousandth one will be without writing them all out? It seems like some kind of magic trick, right? But the secret isn't magic at all. It's math. And it all starts with spotting the pattern. But before we can start predicting anything, we need to be speaking the same language. And that all starts with two fundamental building blocks, the sequence and the series. Okay, first up, a sequence. It's exactly what it sounds like, just a list of numbers in a very specific order. That's it. So, for example, 2, 5, 8, 11, and so on. The only thing you really need to remember here is that the order is everything. Now, what happens if we take that exact same list, but instead of just listing the numbers, we decide to add them all up? Well, that's when you get a series. A series is simply the total sum of all the numbers from a sequence. We're not just listing anymore, we're calculating. So, the crucial point, the main takeaway, is just this simple difference. A sequence is the list itself, and the series is what you get when you add up that list. Getting this straight is the foundation for everything else we're about to do. All right, now that we've got the basics down, let's grab our first major tool for spotting these patterns. This one is all about steady, consistent, predictable change. We're talking about the arithmetic progression, or AP for short. The whole idea here is just simple and steady. In an arithmetic progression, you're just adding or subtracting the exact same number every single time. Take this sequence here, 2, 5, 8, 11. You can kind of feel that rhythm, can't you? We're just adding 3 over and over again. It's like a predictable march forward. So how do we use that predictability to jump way ahead in the line? With this formula. This thing is our prediction tool. A sub n is just the term we're looking for. A is our starting point, the very first number. D is that constant number we keep adding, the common difference. And n is just the spot in line we want to find. See, to get to the nth term, you start at A and you add that difference n minus 1 times. This formula is just a super fast way of doing that. Let's actually try it out. For the sequence 3, 7, 11, what's the 10th term going to be? Well, our first term, A, is 3. And that common difference, D, is 4, right? We're adding 4 each time. So we just plug those numbers in. The 10th term is 3 plus 10 minus 1 times 4. That's just 3 plus 9 times 4, which is 3 plus 36. So the 10th term is 39. And just like that, we jump to the end without having to do all the boring steps in between. Okay, finding a single term is pretty powerful. But what if we need to do something even bigger, like add up the first 100 terms? You could do it one by one, but that is the slow way. The fast way? It involves a really clever shortcut. Some people even call it an Olympiad trick that lets you find the sum almost instantly. And here's one of the key formulas for that trick. It basically says the sum S sub n is just the number of terms, n, divided by 2, and then you multiply that by the very first term, a, plus the very last term, l. So let's find the sum of the first 20 terms of the series that starts with 2 and has a common difference of 3. First, we need that last term. Using our first formula, we find out the 20th term is 59. Now we can plug everything in. 20 terms divided by 2 times our first term, 2, plus our last term, 59. That's just 10 times 61, which is 610. So much easier than adding 20 numbers by hand. Okay, so that was all about steady additive growth. But some patterns, they don't just grow, they explode. And for that, we need our second tool, the geometric progression, or GP. This is the pattern behind rapid, accelerating change. The core idea here is all about multiplication. Instead of adding a constant number, we're now multiplying by 1. So in the sequence 2, 6, 18, 54, each step is 3 times bigger than the one before it. This is where things really start to take off. This is how patterns go viral. And you guessed it, we have a formula to predict the future here too. But notice how it's different. Instead of adding, we're multiplying. And now we've got an exponent in the mix. Here, a is still our first term, and r is that common ratio we keep multiplying by. To get to the nth term, you start at a and you multiply by r n minus 1 times. And that's exactly why r is raised to the power of n minus 1. So let's try this one out. What's the sixth term of 5, 15, 45? Our first term a is 5, and our common ratio r is 3. We just plug it into the formula. That's 5 times 3 to the power of 6 minus 1, so 3 to the 5th. And the result? A whopping 1,215. It just goes to show you how quickly this kind of multiplicative growth can get huge. And yep, just like with APs, we've got a shortcut formula for adding up all the terms in a GP. This is the tool that lets us find the total of these rapidly growing numbers without the massive headache of trying to do it all manually. Okay, let's run through one last calculation. What's the sum of the first 5 terms of 3, 6, 12, question mark? Our first term a is 3, and our common ratio r is 2. So we plug that into our formula. We get 3 times the quantity of 2 to the 5th power minus 1, all of that divided by 2 minus 1. This simplifies down to 3 times 31, which gives us a sum of 93. Okay, we've been through a lot of formulas and examples. But look, this isn't just some abstract math puzzle. Let's connect these ideas back to the real world and see why they actually really matter. This slide right here, this is where it all clicks into place visually. An arithmetic progression with its steady adding always creates a perfectly straight line. It's predictable, it's linear. But a geometric progression, because it's driven by multiplication, creates that famous J-curve, that explosive exponential growth. It starts off slow, and then boom, it shoots for the sky. Understanding this visual difference is the absolute key to spotting these patterns out in the wild. So where do these straight lines and sharp curves actually show up in your life? Well, an AP is kind of like putting the exact same amount of cash into your savings account every single month. A GP, on the other hand, that's the magic of compound interest working on that money. It's also how we model things like population growth. These patterns are totally fundamental in fields like finance, physics, and even computer science. So we've covered the core tools for seeing the future in a list of numbers. Now that you know the difference between adding and multiplying, how would you even start to tackle a problem like this one? It's a great little puzzle to test out your new skills. Give it a shot. Thanks for hanging out with me today, and I'll catch you on the next one.
All right, let's dive right in. Today, we are going to break down 2 of the most powerful and honestly kind of beautiful concepts in all of math. And by the end of this, you'll see the hidden math behind everything from your savings account all the way to earthquakes. So let's get to it.
I know, it sounds like a weird riddle, right? But the answer connects finance, physics, biology, you name it. The secret is this very special kind of growth and decay that once you see it, I promise you're going to start noticing it everywhere.
So the engine that drives all these patterns is what we call the exponential function. You can think of it as the mathematical heart of anything that grows or shrinks based on how big it already is. It's kind of like a snowball rolling downhill. The bigger it gets, the faster it picks up more snow.
What's really cool here is how simple the big difference is. Linear growth is just adding, 2 plus 2 is 4, plus 2 is 6. It's steady, it's predictable. But exponential growth, that's all about multiplying. 2 times 2 is 4, times 2 is 8, times 2 is 16. It starts out slow, and then, boom, it just explodes.
Okay, here's what it looks like formally. Don't let the letters scare you. That A is just your starting point, your initial investment, maybe the initial number of bacteria, whatever. The B, now that's the magic number, the constant multiplier. And X, well, that's just time, or how many times you do the multiplying. This simple little formula is the blueprint for all kinds of runaway change.
So everything hinges on that B value. If your multiplier is bigger than 1, like say 1.05 for a 5% interest rate, you've got growth, things get bigger. But if B is between 0 and 1, like 0.9, you've got decay. That means you're only keeping 90% each time, so the value shrinks. This is what describes everything from your coffee getting cold to radioactive atoms decaying over time.
Okay, so exponentials are fantastic for predicting what's going to happen. They answer the question, if I start with this much and it grows this fast, what will I have down the road? But what if we flip that question around? What if we know where we want to end up, but we don't know how long it's going to take to get there?
Here's a classic example. We want to know how much money we'll have. The base is 2, because it's doubling. The exponent is 3, because 15 years is 3 of those 5-year periods. So 2 to the power of 3, that gives us 8. Easy enough, right?
And here's where we hit a wall. Now we have to solve for the exponent. 2 to the power of what gives us 20? It's not a nice whole number. It's got to be more than 4, since 2 to the 4th is 16, but it's less than 5, since 2 to the 5th is 32. So how in the world do we find the exact answer?
And this is where a new hero enters the story. To solve this exact problem, mathematicians came up with a brilliant tool, the logarithm. It's basically a machine that's built to answer one simple question: how long?
This slide just nails the relationship perfectly. An exponent asks, hey, what do you get if you take 2 to the power of 3? The answer is 8. A logarithm completely flips it. It asks, hey, what power do you need to put on a 2 to end up with 8? And the answer is 3. It's the exact inverse question.
And don't let the notation freak you out. All this is saying is that these two equations mean the exact same thing. Reading log base b of x equals y is just a fancy way of saying b to the power of y equals x. It's the same information, just shuffled around to solve for that exponent.
So let's go back and solve our problem. We were stuck on 2 to the power of x equals 20. While using our new logarithm tool, we just rewrite it. The answer is simply x equals log base 2 of 20. You can plug that into any calculator and get the exact number. Problem solved.
Now for the best part. These two functions aren't just opposites in the questions they ask. They have this deep, really beautiful visual relationship. They are literally two sides of the very same coin.
So first, here's that classic exponential curve. See how it starts off almost flat and then it just rockets straight up towards infinity? That's the picture of that powerful multiplying effect we were talking about.
And now here's its partner. The logarithmic curve does the opposite. It shoots up really fast at the very beginning, and then it starts to flatten out. It'll grow forever, but it slows way, way down.
And this is where it all comes together. When you plot them on the same graph and draw that perfect diagonal line right through the middle, you can see it. They are perfect mirror images of each other. It's just beautiful. Every single point on one curve is perfectly reflected onto the other. They are mathematically and visually a perfect match.
And this whole inverse thing isn't just a pretty picture. It works in the algebra too. If you take the log of an exponential function, as long as they have the same base, they just cancel each other out and you're left with the exponent. And it works the other way too. It's like one is the lock and the other is the key. They perfectly undo each other.
So, why do we care about all this abstract math and mirror images? Well, because these are absolutely essential tools for actually understanding and measuring the world around us, from the tiniest particles to massive global markets.
Exponential functions, they are the language of runaway change. They're how we describe population growth, how your savings account actually works with compound interest, and even how scientists can figure out how old ancient fossils are through radioactive decay. They literally model the processes of the world.
And logarithms? Well, they're the special rulers we invented to measure all that crazy change. You know the Richter scale for earthquakes? A magnitude 7 is 10 times more powerful than a 6. That's a logarithmic scale. Same for decibels for sound and the pH scale for acidity. They help us make sense of absolutely enormous ranges of numbers.
So look, if you remember just one thing from all of this, let it be this. Exponential functions describe wild, explosive growth and decay. And logarithms are the calm, rational scales we invented to tame those wild numbers and actually make them understandable.
And that really brings us to the end. So think about it for a second. Your skills at a new hobby, your social media followers, your knowledge about a topic you love, maybe even the clutter in your garage. Once you learn to spot the pattern of multiplying growth, you'll start seeing it everywhere. So what in your world is on that exponential curve?